Okay, let's start lecture B by looking once more at this example that we just did. I'm going to this example here. And we said this does converge by the alternating series test. The alternating series test can be considered to have something else in it. Maybe not part of the test. It's called the error bounds for alternating series. You can see it on page 518. In the situation where the alternating series test applies, it says that the absolute value of Sn minus S is less than an plus 1. What does this mean? This is the distance between the nth partial sum, Sn, and the sum of the infinite series, S. Sn is the nth partial sum, S is the sum of the infinite series, which you've just proven converges by the alternating series test because it fits the alternating series test. And this, well, that's just the n plus first term. Well, not the n plus 1 first term, but the a that's next to the n, negative 1 to the n minus 1 in the n plus first term. So it's not. Ignoring the sign. Let's just phrase it that way. It is a positive quantity here that I'm talking about. This is positive. I'm not sure the best way to phrase this is. This is positive. So, for our example, this can be simplified to S, the distance between Sn and S is less than 1 over square root of n plus 1. And this is actually a pretty useful thing. If you wanted to approximate this series, its actual value, to within a certain amount, if your goal is to approximate S to within, for example, 10 to the negative 4, 0.0001. What you could do is this inequality guarantees that if you set this expression equal to that or less than that, you can solve for an n that will work. 1 over square root of n plus 1 equals 10 to the negative 4. You can solve for a minimal n that would be guaranteed to work. Now, you might be able to get away with a smaller n, but this will be an n that's guaranteed to work because this inequality is guaranteed to be true. Solve for n here, take the reciprocal of both sides, then take the square root of both sides, then subtract 1. It looks like n equals 99 was enough to get us within 10 to the 4th, which 10 to the negative 4, which seems a little odd based on the
square both sides?
Oh yeah, thank you. I thought that seemed too small. Yeah, n plus 1 is going to be 10 to the 8th. N is 10 to the 8th minus 1. That's better. 10 to the 8th is 100 million. So we're talking 99,999,999. Or you might as well just round up to 100 million. It's going to take 100 million terms to be within this much of the actual value. Guaranteed. You might be able to get away with the smaller n, but if you want to guarantee, you got to go that big, according to this inequality. So yeah, the convergence of this is very slow, is the point. Let me do one more, or maybe two quick examples. Think briefly about them, and then we're going to move on to power series. If you've got a series that involves the natural log of n, for example, this one, oftentimes the best thing to try to use is the integral test. Let f of x be natural log of x over x. Graph it from 1 to infinity. It's not always decreasing, but it would be eventually decreasing on the interval from 1 to infinity. It's probably going to look about like this. And in the integral test, I'll just tell you, you can get away with your function just being eventually always decreasing. It doesn't have to start decreasing at 1, and the integral test will technically still apply. Then I figure out where that maximum is. Yeah, I can differentiate it to figure it out. I'm not going to worry about it. I'm just going to say the graph looks like that. So it's a situation where the integral test would apply. You could try integrating this function from 1 to infinity and see if this integral converges or not. To do that, actually, it's best to use a substitution. If w is natural log of x, dw is 1 over x dx, you'd really be integrating w dw. When x is 1, w is natural log of 1, which is 0. As x goes to infinity, log of x still goes to infinity. You'd have to try that integral, and I hope you see, just looking at that integral, that it would definitely diverge. So this series diverges. The divergence test doesn't work, though. The terms here do go to 0, slowly, but they do go to 0. N grows faster than natural log of n does. So the terms go to 0, so the divergence test does not apply, but if you use the integral test, it does apply, and this improper integral diverges, which would mean this series diverges. You also could do the comparison test here, too. Natural log of n over n will be greater than or equal to 1 over n if n is greater than or equal to 3. And we know this series, that series diverges. It's the harmonic series. Therefore, the comparison test and this inequality would imply that this series diverges as well. You could use the comparison test there. That could be one I'd put on the test and maybe say prove it. So you'd have to write out sentences. Call that an, call that bn. This is clear that this is true, as long as n is bigger than or equal to 3, because natural log of n will be bigger than or equal to 1, as long as n is bigger than or equal to 3. Natural log of e is 1. Natural log of 3 is bigger than 1. It's same for all other natural logs of n when n is bigger than or equal to 3. So I said that kind of fast. Watch the video if you want to recapture what I said. The comparison test can also prove this diverges. You might wonder if a series like this would converge or diverge. And there, the comparison test really can't be used, at least not if you're comparing it to the harmonic series, because these terms are going to be less than 1 over n when n is bigger than or equal to 3. The inequality would go the wrong direction, because we're divided by the natural log of n there. So they're probably almost guaranteed the best thing to do is the integral test. And I suppose I should also technically start at n equals 2 here, so I'm not dividing by 0. Natural log of 1 is 0. Graph that function, it does decrease. Actually, we have a vertical asymptote at x equals 1. Graph would look like that. You'd want to integrate 1 over x times natural log of x. The same substitution would work here. W is natural log of x, dw is 1 over x dx. And what you would be integrating would then be 1 over w. And we could do a 2 here. Say from natural log of 2 to infinity. And that would be a divergent integral too, though not as obviously divergent as the other one was. Try to do this improper integral, you'll get another natural log involved, which will go to infinity as w goes to infinity. So this is still going to diverge with the upshot. This improper integral will diverge, this series will diverge. Dividing by natural log of n is not enough to make the terms go to 0 fast enough to make the series converge. Which is interesting when you also compare it with something like this, for example. say you did 1 over n to the 1.000001. Those terms don't seem to go to 0 very fast either. Emphasis on making this number just barely above 1. However, it is a p-series with p equal to this, which is technically bigger than 1, so this technically does converge, though very, very slow. All right, let's go on to power series. This is section 9.5 now. A power series centered at some number is the way it's said. And different letters are used by different books. What letters our book use? Our book uses A. Centered at x equals A is a series of the form summation. It's traditional to start the summation at 0 with power series. I could use a k, I'll use an n this time. N goes from 0 to infinity. C sub n times x minus a to the n power. And it's because that is a power that this is called a power series. You write this out. When n is 0, you get c sub 0, x minus a to the 0 power, which we take to represent 1, though even though 0 to the 0 power is undefined. So if x was equal to a, you get 0 to the 0 power, which is technically undefined, but don't worry about it. It's not perfect notation, is kind of the upshot. It breaks down when x equals a and n equals 0, because then you get 0 to the 0. But we just don't worry about that. That slight bug in the ointment there. Then n is 1, then n is 2, then n is 3. These are all a's, by the way, they're not 9s. Etc. It's called a power series because it's a series of things involving power. That's why it's called a power series. As it is, it's just an expression. In general, we would plug in numbers for the c's, or Cn would have a formula that would give us numbers for different n's. And we plug in something for a. And we could plug something in for x, but we often will treat x as a variable. And think of this as a function of x. That'll be what we most commonly do, but we certainly can plug in specific values of x. And it might converge for certain values of x and diverge for other values of x. Here's an example. Well, in this example, I'm going to start. Let's just do it this way. There's a power series, an example. If you wrote it out, it would be 1 plus 1/2 times x minus 3 plus 1/3 times x minus 3 squared plus 1/4 times x minus 3 cubed plus 1/5 times x minus 3 to the 4th, etc. See how that works? When n is 0, you get a 1 down there, you get a 0 power right there, which we take to give you 1. When n is 1, you get a 2 down there, a 1/2, being multiplied, and a first power there. When n is 2, you get a 3 down there, equivalent to multiplying by 1/3, and a 2 up there, matching the 2 there, etc. There's an example of the power series. Does it converge? The answer is it depends. It depends on what x is. It converges for some x's, but not others. How do you decide what x's it converges to? What x's it converges for, I should say. The best thing is to use the ratio test, typically. Limit as n goes to infinity of the absolute value of an plus 1 divided by the absolute value of an. Here you really do need the absolute value signs. They are essential to be there this time, because this quantity could be positive or negative. That is your a sub n. It's the terms you're adding. So this time you have to leave the absolute value signs in there. But that's okay. It's not as bad as it sounds. One thing that makes it a little simpler is the ratio of the two absolute values is the absolute value of the ratio of the things inside. So you can just put one set of absolute value signs. Makes it a little simpler. What's a sub n plus 1? It's this with n plus 1 in place of n. X minus 3 to the n plus 1 divided by n plus 2. Divide by a sub n divided by that is the same as multiply by its reciprocal, so I'm really skipping a step here to write this. So I skipped a step there. I really want this thing with n plus 1 in place of n divided by the same thing with an n there. But dividing by a fraction is the same as multiplying by its reciprocal, so I just skip to the multiply by the reciprocal step. Can this be simplified? Yep. This is the same as x minus 3 to the nth power times x minus 3. The x minus 3 to the nth powers cancel. The n plus 1 and n plus 2 are still there, and we also have an x minus 3 still there. What's the best way to write this? Question?
Yes. When you were doing the x minus 3, how did you get the factorial?
I didn't get a factorial. There's no factorial here.
It looks like there's an exclamation mark next to that x minus 3 that you crossed. Yeah.
Yeah, that's a times. That's an n there and a times. X minus 3 to the nth times x minus 3. It's not an exclamation point.
Okay.
Thanks for seeing that. You can write it like that. Technically speaking, you can also factor out the absolute value of x minus 3 because it doesn't depend on n. And that probably would be a good thing to do here. So this will equal the absolute value of x minus 3 times the limit as n goes to infinity of the absolute value of the ratio there, though n is greater than or equal to 0, so this is a positive quantity and the absolute value signs can go away. That won't always necessarily be the case, but it is here. This limit is 1. So the answer is the absolute value of x minus 3. That's this limit. It's dependent on x. It depends on what x is. What do we say for the ratio test? The original series would converge if this limit is less than 1. It will diverge if the limit is greater than 1. And if the limit equals 1, there's no information provided. So what we can conclude is that the original series here, the original power series, converges if that thing that we got from the ratio test is less than 1. Diverges if that thing is bigger than 1. And if it equals 1, the ratio test provides no information. No info from ratio test, at least, if the absolute value of x minus 3 equals 1. Thinking now of x as being a variable, you can can interpret these inequalities in terms of intervals on the number line. Focus on the one where it converges. That's the set of all values of x that are a distance 1 away from 3. Less than 1, I should say. So if you draw 3 on a number line along with 2 and 4, definitely for x values between 2 and 4, strictly speaking, between 2 and 4, this series back here will converge. And definitely for x bigger than 4 or less than 2, the series will diverge. What about when x is 2 or 4? You have to treat the endpoints of the interval here as special cases that need to be considered separate. If x equals 2, for example, what does the series become? Plug in x equals 2 there, you get 2 minus 3 is negative 1. You get an alternating series. And it converges. By the way, the alternating series that you might happen to be looking at doesn't have to necessarily conform exactly to the form in the alternating series test. In the alternating series test, the signs alternate plus, minus, etc. But your series could start minus, plus, minus, plus, minus, plus. And you can still apply the alternating series test. This one, since we're starting at 0 and have an n there, does start plus. In fact, this is the alternating harmonic series here. If I remember right, the alternating harmonic series, I know it converges. I think it converges to natural log 2, amazingly enough. Let me test that quick. I'll type it in here as I wrote it on the board just now. Oops. I think this is going to be log 2. Yep, I remember correctly. Alternating harmonic series converges to natural log 2. This is a natural log. Mathematica does log it. Natural log as log. What if x is the other endpoint, 4? If x is 4, what does the series become? Replace the x with a 4 here. 4 minus 3 is positive 1. The n is positive 1 still. I get the harmonic series, which you should always remember for the rest of your life. That diverges. You should never forget that.
Isn't the harmonic series just 1 over n? Or is 1 over n plus 1 also a harmonic series?
It's the harmonic series because I'm starting at n equals 0 here, and it's the same infinite sum as if we start n at 1 and have a 1 over n. Yeah.
Okay.
You can write these series in different ways, but they're the same series.
All right.
Yeah, you should remember that for the rest of your life. I should test you when you're 80 years old. Does the harmonic series converge or diverge? It diverges. You should remember that. Okay? So actually, this power series converges on an interval from 2 to 4, including 2 but not including 4. Kind of strange. The so-called interval of convergence looks like that. In interval notation, you put a square bracket next to the 2, you put a parenthesis next to the 4. We include the 2 but not the 4. With inequalities, you'd write 2 less than or equal to x less than 4. These are different ways of representing the interval of convergence is what this is called. The interval of convergence is centered on A. The 3 is the A. 3 there is like the A there. So I guess if that's the center of the interval, Don't worry about whether the endpoint is included or not. I guess the interval's got a radius. You know, the radius of a circle is the distance from the center of the circle to the edge. Whether you include the edge as part of the circle or not, I should really say part of the disk or not. Circle technically only refers to the curve, whereas a disk refers to the inside of the circle. It's got a radius, distance from the center to the edge. That radius is 1. It's called the radius of convergence. You might scratch your head and say, well, should you really use the word radius since there are no circles here? And my answer would be, yes, you should still use the word radius, because if we considered x to be a complex number involving the imaginary unit I, and you graphed it in something called a complex plane, it really would be a disk, what's inside a circle, and it really would be a radius that this series would converge on. We're not going to go there, other than me just saying it right now. Actually, I probably will talk more about complex numbers in chapter 10. Just can't avoid it, it's just so beautiful. Okay. But for now, we won't. We will go ahead and call this a radius. That's a radius of convergence. It's that distance. It's also the distance on the other side. Again, not worrying about whether the endpoint is included or not, just focused on the distance between the center and the endpoints of the interval. Called a radius of convergence. The entire interval itself is called an interval of convergence. Question?
Yeah, so with our test, we don't know if it's equal to 1.
The ratio test tells you no information,
But actually plugging in numbers, we can tell.
other tests help us tell, like the alternating series test, for example.
Okay.
The ratio test is kind of fun to use in a way, but there are plenty of examples where it gives you no information. Like p-series, for example, I mentioned that the other day. The ratio test doesn't tell you about convergence of p-series. So it's not a super strong test. It's not as strong as some other tests. Oh, how are we doing in time now? Let's see. Let's do one more quick example. Oftentimes, A is taken to be 0. So I'm just going to write an x to the n, which is the same as x minus 0 quantity to the n. I'm going to divide that by n factorial. Remember that 0 factorial by definition is 1. And part of the reason is so this formula works out nice. It's not the only reason. So when n is 0, I get x to the 0, which is taken to be 1, even if x is 0, but that's technically not correct, but don't worry about it. 0 factorial is 1. When n is 1, you get x to the first over 1 factorial. 1 factorial is also 1. When n is 2, 2 factorial is 2, so you get x squared over 2 factorial. I'll just write it as a 2. Well, let's go ahead and write it as a factorial, 2 factorial, etc. Three factorial is 6, 4 factorial is 24, 5 factorial is 120, etc. You can figure that out. What's the interval of convergence and radius of convergence for this exam? Use the ratio test. Limit as n goes to infinity of the absolute value of an plus 1 over the absolute value of an. You do need to keep the absolute values in here for these power series. You can put the absolute value on the whole thing. When you replace n with n plus 1 here and here, you're going to get x to the n plus 1 over n plus 1 factorial. Divide by this thing with just the n there as it is, multiply times its reciprocal, As usual, the n factorials cancel to leave an n plus 1 right there after cancellation, because that's n plus 1 times n factorial. And the xn's will cancel with all these except for one of them. You'll be left with just one x. You can pull the absolute value of x in front, and here's what you're left with. You can get rid of the absolute values around n plus 1. And no matter what x is, this limit is 0 for all x. 0 is less than 1. So the ratio test says that this series converges no matter what x is. For all x, it converges over the entire real number line. No matter how big x is. It's pretty amazing if you think about it, because we're dealing with arbitrarily high powers of x. If you're plugging in x equals a Google, somewhere in there you're doing x to the Google power, so you'd have a Google to the Google power, a Google plus. That's what it's called. But the fact that you're dividing by these factorials and the fact that they grow so big so fast is enough to still make the series converge, even if x is humongous. The interval of convergence is the entire real number line. If the series centered at 0, what's the radius? I guess you should call it infinity. R equals infinity. And that's what people do. Give me 10 seconds. Amazingly enough, we're going to see in chapter 10 that this series equals e to the x for all x. And that's going to be like the highlight of what we do with power series and Taylor series. Amazingly enough, this equals e to the x for all x. X can even be a complex number and it still works. Don't worry about what that means right now. Okay? See you next time.